Hi, this is Engineering Mechanics Dynamics. I'm Dane Quinn from the University of Akron, and today I'll do another example with planar kinematics. We have a point P that moves with constant velocity relative to this disk. So P moves along this slot, and we assume the motion is constant velocity. So the velocity of P relative to the disk is minus v in the E2 direction. Again, if v is positive, it's moving sort of down along the slot like this. However, the disk spins with angular velocity omega k, and we assume that the angular velocity is constant with respect to the ground. So what I'd like to do is find the acceleration of this point with respect to the ground as it moves along the slot. So I want to do this as a function of z, which measures, of course, the position of p along the slot. The slot is offset by a distance d relative to the center. And I'll define directions I and j fixed in the ground, and then E1 and E2 that are fixed in the disk. So this problem is similar to a person walking along a carousel. So you can imagine a big carousel, and it's spinning along at constant angular velocity. And then if you're on the outside and you want to go see someone, say, toward the middle, right, you might try to walk in a straight line relative to the carousel toward that individual. And so what I'd like to do, again, is find the acceleration, not with respect to the carousel or with respect to the disk in this case, but the acceleration of the point P with respect to the slot. So really, we'll just use our equations of planar kinematics, noting that point O is fixed in the ground. So we know something about the motion of point O. Again, we know a lot, actually. It's stationary. It has zero velocity, zero acceleration with respect to the ground. And we know the motion of P relative to the disk. So we can relate the acceleration of O and P. And we'll do that with our kinematic relationship that says the acceleration of P is the acceleration of O plus the angular acceleration of the disk cross RPO. That's the position of P with respect to O. So again, here in the figure, RPO would be that vector. And then we have the angular velocity of the disk cross the angular velocity again and the position. And then finally, because P is moving in the disk, we have two additional terms. One is the Coriolis term, which is 2 omega cross the velocity of P with respect to the disk. And this is very important. This is not the velocity of P with respect to the ground, but it's the velocity of P with respect to the disk, which was given to us in the problem statement. And then finally, we have the acceleration of P with respect to the disk. So all five of these terms combine to give us the acceleration of P with respect to the ground. So really, this problem is just about going through and identifying what these individual terms are, and then using this relationship to relate the velocity of O, the dynamics and the kinematics of the point P with respect to the disk, to find the acceleration of P with respect to the ground. So now, let's look at these terms. The acceleration of O is 0. Again, O is fixed in the ground. Right, so that's easy. The next one is the angular acceleration of D, the disk. Well, the angular velocity was constant, so that means the angular acceleration also vanishes. So moving along, let's look at the next term in line. That's the position of P with respect to O. Well, that might be a complicated function in terms of directions I and j, but in terms of directions E1 and E2, that's actually relatively simple. If I want to go from O to P, I will go a distance d in the E1 direction, and then I'll go a distance of z. That's the coordinate that describes the change in the position of P along the slot. in the E2 direction. So this is simply d E1 plus z E2. And of course, the angular velocity was given to us in the problem statement. That's omega k. And notice in purple, I've sort of tried to identify the different variables that are assumed to be known. Right? So I assume that we know the angular velocity. I assume that we know the velocity along the slot. And I want to find this in terms of the displacement of p along the slot, which was measured by z. So again, the angular velocity is known. We've already found that. The velocity of p with respect to the disk is given in the problem statement. And then finally, the acceleration of p with respect to the disk vanishes because the velocity with respect to the disk is constant. Even though we'll find the acceleration of p with respect to the ground, that's a different frame of reference, is not constant. So now we need to simply plug all of this in. So we have 0 plus 0. So alpha cross r is 0 because alpha is 0. Then I have omega k, the angular velocity, cross omega k cross rpo. So that's d in the E1 direction, z in the E2 direction. Moving along, the next term is 2 times omega k cross the velocity of p with respect to d. So that's minus v in the E2 direction. And finally, we have 0 because the acceleration of p with respect to the disk is 0. And now I need to evaluate these terms, and in particular all of these different cross products. So looking at this last term, k cross E2 is minus E1. We have another minus sign there. So we have 2 omega v. Now for this first term, k cross E1 is E2, and then k cross what ends up being E2 is minus E1. So again, in the E1 direction, we also have a term that looks like minus d omega squared E1. And then finally, k cross E2 is minus E1, and then k cross E1 is E2, but we have the minus sign there. And again, if you want to pause this and work this out, that might be a good idea. So in the E2 direction, we have a term that looks like minus z omega squared E2. So here, this becomes the acceleration of p. And notice that it's defined simply in terms of the directions E1 and E2 that are fixed in the disk. So if I wanted to find the acceleration of p with respect to directions fixed in the ground, I would have to determine where E1 and E2 were, right, at whatever instant in time, based on the rotation of the disk, and then write those in terms of I and j. But really, we can completely define the acceleration in terms of E1 and E2. So that's it. Right? Again, this is a fairly simple example, pretty quick actually, that allows us to relate the acceleration of a point with respect to the ground to the acceleration of a known point, the dynamics or the motion of the intermediate frame of reference, in this case the disk, and the motion of the point, p, with respect to that intermediate frame of reference. Again, how p moves with respect to the disk. So that's it. Thank you very much, and I will be back with more examples.